section on the endogeneity problems, right? So basically, to talk about what is the problem, basically the assumption here is that the assumption number 3 doesn't hold. Right? So what is the consequence? And this is what the consequence of endogeneity that can arise. So let's firstly what we mean by an endogenous variable. An endogenous variable is a variable that is correlated with the error term. So an example when we estimate an equation that suffers from the problem of endogeneity is when you want to estimate the impact of education on wages and salary. Right? So people who, let's say, the problem of endogeneity arises because the problem of endogeneity arises because of the problem of the so-called problem omitted variable.
Recording in progress.
So what do we mean by omitted variable here? So people differ in their unobservable characteristics. So someone who have a strong characteristic in terms of studying often also is someone who knows how to make money and who earn more than the others. That is a kind of ability that is hidden. How can we measure the ability of individuals? That is very difficult. Right? The people have tried to find ways to do that. They may measure the IQ test that a person may take. The problem is, if you take the IQ test on someone who have done the IQ test many times, the result is very much different from someone who have seen it for the first time. And I think mostly in order to test it, either you have the people who have the equal amount of training or nothing at all in order to test it, to make it, to measure the individual characteristic. So most of the time we cannot measure that. So in the error term, the variable that represents the individual characteristic is there, right? So it is correlated with education. And so when you regress education on wages and salary on a set of control variables and education is correlated with the error term, and the estimated results could be wrong. Right, so this is what you will see, right? So let's say if you have the beta OLS estimated using the OLS method, you can rewrite the model in this way, and after some, let's say, if the correlation between x and epsilon is eta, after some manipulation, you will see that the result is equal to this one. So the OLS estimate is equal to beta plus the last component of this one, right? The components of the last column of this matrix. So you see that even though only the last, let's say some of the columns of x's are endogenous, the estimated coefficient, the whole vector here is contaminated. So the bias will happen not only to the endogenous variable, but also to other variables. The coefficient of the other variables, right? So this is quite a problem, and it is known as the smearing effect. Are you with me? Yes, I'll say it again, right? I say it again. So the story I was telling before Tang Li came was if we have a linear model, and but the problem, there is a problem of endogeneity, meaning that at least one column in the X is correlated with the average. If that is the case, if we run the OLS model, we follow the OLS estimate and we take the expectation of beta OLS given X, right? So when we say expectation of beta OLS given X is what is the average value given the contribution of all observations in this data set on the beta hat. And if we sum the contribution of all of the observations in the data set, we will see after summing manipulation that it is equal to the true value of beta plus a column. You see, this is a matrix times a vector that has only the last column as 1. So you have the last column of this matrix times eta, right? That is to say, it will be wrong not only for the last variable that is endogenous, but the coefficient of other variables are also influenced and wrong. So this is the problem, right? So if this is the case, then what is the solution, right? So the solution here, let's say before we talk about the solutions, let's think of, let's say, what are the possible causes of endogeneity, right? So one is the omitted variable I have just explained. The other is measurement error. So if there is measurement error, the variable with the with the error and measurement error is also endogenous. If there is simultaneity, that means in order we call it reverse causality. So x and y, some of the x and the y belong to a kind of a system that you know one, you know the other. For example, if you talk about supply and demand, right? Supply and demand. So supply and demand are two variables. Which one causes the other, we do not know. So the demand will lead to higher price, right? And lower price will lead to more demand, for example. So in this case, price and demand, higher demand will lead to higher prices, but higher prices will lead to lower demand. The causality is both ways. Right? So how to solve this problem? We need to find a set of instrument Z, right? The instrument Z must satisfy two conditions. One is that it is relevant. The other is that it is exogenous, so that the variable, the instrument Z must be independent of the error term. While the relevance can be tested, let's say we regress the endogenous variable on the instruments, and if the f-test is large, or the t-test is large, we say that the instrument is relevant. But for the exogeneity, we cannot test, because all the time, the OLS residual is orthogonal to the explanatory variable. So let's say the only way to convince someone that Z is a valid set of instruments is to argue verbally. For example, one is that to convincingly rule out any direct effect of the instruments on the dependent variables or any effect running through omitted variables. This is the exclusion restriction. Convincingly rule out any reverse causality, and convincingly explain why instruments influence the endogenous regressors. This is the influence after controlling for the effect through other exogenous variables. So if you do not understand why why excluded instrument and endogenous variables are correlated, then there is a correlation is likely a sign that either A or B is violated. So basically, we have to argue. For example, this is an example of an argument for the exogeneity of the events. So there are two economists. One is Anna Kruger, the other is, I think the name is somewhat, but Anna Kruger was a lady who wanted to explain the impact of occupation on wages and salary. So they exploit the one social experiment that in the United States, some states regulate that if you were born after June, you have to go to school with the ones who were born in the next year. Okay, so they argue that if someone who was born in the third and the fourth quarter, he or she will have to go to school 1 year later, in comparison with someone who was born in the first and second quarter. So this is by law. But because you go to school later, because when going to school you depend on the others for the financial support, the likelihood that someone will drop out of school is higher if someone is born in the third or fourth quarter. So they use the instrument that is the quarter that is born, okay, as an instrument for the years of education. So they argue that it will be that there will be a negative relationship if you quote the quarter of that person was born from 1 to 4, then there could be a negative correlation between the years of education and the quarter at this point. And the argument is, people who born at different quarters, there is no evidence that someone who is born in the first quarter will be smarter than someone who is born in fourth quarter. So it cannot cause the wages and salary. There is no correlation with the error term, right? And it is high correlated because, and the rule out of causality, let's say, higher quarter of birth, right, lead to lower education. But lower education will not be able to decide when you were born. So there is no causality, reverse causality, right? So this is the idea that she used that one, and that example has become a classical example discussed everywhere when it comes to endogenous. And the conclusion was, if you go for 1 more years of education, generally your wages and salary will increase by 3%. Yeah, 3%. That is quite large over the lifetime. And if you take a GRE, so your wages and salary will be 6% higher on average. Maybe you will have 10% or 15%. Okay, good.
So the IV variable we can choose like to have the negative correlated with the x, right?
Negative or positive, it depends on whatever. As long as it is highly correlated, it's fine. Yeah.
Cái IV là nó phải correlate với cái ít là Y nó sẽ cộng 1. Y là
Convincingly rule out any direct effect of the instrument on the dependent variable. Mình rule out. Có nghĩa là cái instrument nó có được tác động lên Y không?
Không.
Không. Cái quý mà em được sinh ra cũng không tác động đến cái lưu em kiếm sau này. Nó chỉ qua cái tác động của em đi học hiểu ấy là tác động lên lương họ. Okay. 100% sure. Now and forever. Okay. Good. Okay. So the instrument cannot be correlated with the dependent variable, the instrument, right? So the quarter you were born will not be able to determine how much you are. But it only works through the number of years that you go to school. Okay? That's that. So this is the condition, and if these conditions are satisfied, then we will say that this is something about the law of large number. You will see that we will follow the trick in the morning. You have the y equal x beta plus epsilon. Then you pre-multiply by z transpose, right? And after some manipulation, you come up with the transform variable. This variable transformed by, you take the z, the instrument z, side of the regression equation. Then you come up with a new regression model that is transformed. The problem is when you transform, like even though in the original regression model, epsilon is normally distributed, is IID. But if you transform the model, the epsilon star here is no longer epsilon, but it is z transpose times epsilon. The variance of epsilon star is now sigma squared times z transpose z. So it is homoscedastic. It's no longer I here. So let's say, again, we would decompose the z transpose z into a form of pp transpose. This morning I talked about that already. Okay, if we do that, we will apply the so-called GOS this morning, right? In this equation, we would multiply y star by b to minus 1, b minus 1 x star beta, b minus 1 times epsilon hat. We call it y tilde, x tilde, and epsilon tilde. Right? You may check that the expectation of epsilon tilde transpose is now an identity matrix. Yeah, so it is homoscedastic again. Right? If it is homoscedastic, and the model again, when the error term satisfies this condition, we say that the error terms are spherical. Fair enough? The transform model now satisfies the 6 assumptions of the OLS model. And we apply the OLS to equation number 6 and we deal this one. So this is the beta IV, right? So we just apply, now we have the model here. Because the model here now satisfies the condition that it is homoscedastic. And because of the transform, it is also exogenous, right? So after some manipulation, you will see that beta IV is equal to x tilde transpose x tilde, x tilde transpose y tilde. You know that x tilde is b to the minus 1 times x star. X star is nothing more, so let's say after some manipulation, we will see that it is x star transpose some pp transpose to the minus 1 times x star. Remember that x star is nothing more than z transpose times x, right? So we multiply it out and we group them together. You will see that there is z times z transpose z to the minus 1 z transpose times x. This is PZ, the projection matrix on Z. This is also PZ. So if you write it again, you see that x transpose PZ times x to the minus 1 x transpose PZ times y. This is nothing more than, what is it here? You take PZ times x, that is project x on the Z, get the predicted value, and regress again. This is the idea. I think you know very well from the Windows course, right? This is the way we derive it?
Yep.
Okay. So it's very clear. So you come to the idea of two-stage this way. Very fast, right? Good. Okay. So we know the algorithm, right? We know the algorithm. Then you know the variance and the algorithm in this way. So now, if in the examination the question is manually estimate the two-stage, this is what I expect you to do, right? So what I'm going to do, you just follow the steps, and you will be able to compute it. Now, I come to the final point here, and then we are done. That is to say, sometimes there is a problem that observations in the same area or in the same group may have their error terms correlated with each other, right? For example, people in the same village may have higher or lower income, simultaneously because of natural causes. For example, if you have the catastrophe that destroy all of the crops, everyone will be poor. Everyone will consume less per year, right? Or if you may have other shocks. So let's say in that case, in our regression that we are studying so far, there is a probability that, so let's say in our data we are talking about, what's that, the clothing expenditure. In a village, if everyone dressed the same, there is no tendency that people to change, right? But if someone started to dress beautifully, there is a tendency others will follow. That's the trend. Is that right? So it could be the case that in the same commune, in the same village, there could be some movement that lead to, if someone spend a lot on clothing, the others will follow. Okay, so in that case, we will follow the same logic that like this morning. So we would allow for the error term to be correlated between the individuals in the same group. Okay, so we construct the new, let's say this is a sandwich again. We will, let's say in our case, we will count how many villages are there. Village in that data set is địa bàn, tỉnh, huyện, xã, địa bàn, hộ số. Okay, so địa bàn is like a village, like a quận, tổ, phường gì đó. Là họ đi điều tra cả một cái làng đó, hiểu không nhỉ? Cả một cái địa bàn đó, cả một cái khu phố đó. Okay. So let's say this is a way to compute. This is a kind of serial correlation that is different from the serial correlation that we talk in the morning. In the morning it was time series. In the afternoon it is spatial dependence. Spatial dependence, meaning that people have the same space. Right? If that is the case, we also have to compute the new variant matrix, and I have made a computation here. Right, so let's say again, I would ask for your support in doing the so-called eyeballing methodology. So this is what I did with the instruments, right? And then I would compute the ID model, and I compute the standard, the cluster robust standard error. Right? So this is something you should look at. For example, they would have to first you have to define the cluster. What do you mean by the cluster? The cluster defined here. Add to ID, right? So let's say add cluster ID, so have DF cluster ID is equal to tỉnh, huyện, xã, địa bàn. You add together. So it will be a string of variables that would uniquely identify the địa bàn. And everyone in the địa bàn would have to set up a matrix. So let's say you have each person in that địa bàn has one row, right? So you allow for the error term to be correlated. So you will calculate the covariance, the error term within that địa bàn, and you allow it to be correlated. People outside of the same địa bàn would have zero. You don't care about that. Okay, so this is how it is done.
Can you draw a simple, not so large matrix to illustrate that? So there would be some entries off the diagonal.
Yeah, let's say it this way. So you would expect to have, let's say in a let's say a village, right? So person in the same village, you should say village 1. Okay, village 1. So let's say in this case G equal 1. You have 15 households. Okay? You would first estimate for the error term for the first one. You would have epsilon hat 1 square. Okay? Epsilon hat 1 2. 1 here is the village, 2 is the household square. Right? You go down here. You have epsilon hat 15 square. Okay? For each people in this group, what do? You would have the summation for t equal 1 to 15, okay, of xt transpose times epsilon 1 t square. This is a k by k. This is the error term. So for this village, you have one matrix. Okay. So you have one matrix, and now you will have many villages. Is that right? So you will, for each village you form one k by k matrix, and for all you will take another sum here. Okay. For G equal to 1, G here is the group. Till say let's say till say I put it G. Okay. So instead of having the 1 here, I would have the G here. Okay, the G here and the G here. So it will kind of add all of them together. So you have a kind of a new kind of. So this is the inner part. Okay? You do it for all communes, all villages, all words, and then you put x transpose x to the minus 1 over here. Is that right? Actually, it is x hat. Right?
I think can I ask another example? Like, if we define only one type of cluster, for example, like, what do you say, just like physically the area, but maybe I'm from cluster 1, but I study in the same school with people from other clusters. So how can we like create such like larger dimensional covariant invariant matrix to represent different type of cluster we can have at the same time?
That will enter the realm of so-called spatial econometrics. Yeah, so that would be the spatial, what do they call it? A spillover and the like. Yeah, but that will be beyond this one. So in this one, we are assuming that people in the same group have kind of are correlated in their error terms. Okay, let's say. This is a very tough question. I know that there was some people who do the study on this one, but let's say the problem of spillover is there, right? So let's say if this is a village, the next village, if everyone on this side dressed beautifully, there's no loyalty, and the other one on the same status, right? There will be the spreading. Yeah, but let's say in this context, something that we can know quite for sure is if the village is selected here, it is very much unlikely the next village is selected. It could be kilometers away because we select just of the 25 million Vietnamese households, we only select something like 45,000 over 25 million. That is to say about 1 in every 6,000 households would be selected, right? So the probability that two villages, two adjacent villages are selected, there is no guarantee that they are not. But randomly, they could be, right? But that would be very rare. Good. So let's say the probability that this household, this village is selected is 1,000, and the next one is selected is another 1,000. If it is independent, the probability that both of them are selected at the same time is 1 over a million. That is rare, but it could happen. Who knows? Good. Agree? But this is the idea of the cluster. You get it? Yeah. So in the morning, we do not care about the cluster. We sum all xt transpose with the epsilon hat t squared. But now we do it for each group, okay? And then we sum them together. So for each village, you have one sandwich, one middle part of the sandwich. You put them all together, you have a big sandwich. And you wrap them with the x hat transpose x hat to the minus 1. Of course, I am lazy, but we do know that there must be an x transpose to the minus 1 here. And this one is something like an omega. Right? That's the idea. So how to implement that? In this area. Good. So with that, I still have something to move on, right? So I will leave the panel econometrics models for you to study. Yeah, I'll give you the algorithm, but it's very simple. So when you have the panel, another kind of cluster over the same individual, but over time. Is that right? Because you have panel, you mean that for one unit you have the repeated observations over time. So the idea is you must do something, and you can exploit the panel structure, and you can sometimes get rid of the problem that we are suffering in the cross-sectional setting. Let me give you an example. Then you will see that how the panel can be the panel structure can be exploited in order to answer some of the very interesting. This is an example I want to talk about. You want me to write with this color? Hello? Let's do it with a different color, right? And do it with this one. So, the one who cannot read my writing here is the one who was with me, right? So, don't you see anything? Okay, now I'm writing it this way. So let's say you have y1t, that is the first person, okay, equal to x1t transpose beta plus epsilon 1t. Fair enough? So by x1t here, transpose here, I mean I have a row. Right? Now, let's say I take the row of the explanatory matrix times the column of the coefficient. Actually, I would have it equal to x1t beta 1 plus x2 t beta 2 plus x 3t beta 3 and so on and so forth. Right? So this one is nothing more than the way to write the row of the regression model. This is one row. Fair enough? Are you with me? One row. Is it okay?
Yeah.
So if I have the second observation, so now I want to make it explicit here. I have a second observation y1t plus 1. You get it? So this is the same person, but now the time is t plus 1. Equal to x1 t plus 1, of course, transpose beta plus epsilon 1 t plus 1. Okay? I can do it until y1t, is that correct? Equal to x1t transpose beta plus epsilon 1t. Fair enough? Okay. So this is, let's say in one of the axes, we have measure that is education. Now, and in the epsilon t here, we have a problem that we cannot measure, so we leave it in the error term, that is the ability. Right? So I write the ability explicitly. I will write the ability variable explicitly. Let me choose the pen. Which one you want? For the bachelor, I often take the purple color, or let's say the violet color to talk about love. But for you, some of you is appropriate, but some is not, right? So let's say in this case we say that it is the ui. This one is equal to ui plus zeta of c I t 1t. Okay. So this is u1. U1 here is the specific effect of that person. You would have it, this is U1 plus C1T plus 1. Fair enough? And dot 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 here you have U1 C1T. Right? Okay. So of course I will have the second observation. It will be y2t dot 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 until y2t. Fair enough? So there is a way that I can get rid of this kind of, I want to be explicit here. This is u2 plus epsilon with c 2t dot 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 until u2 plus c2t. Is that right? Okay. Now, so we are talking about something we know. Now, if I take the average of all of these observations over the individual one, if I take the average, what do I get? If I take the average, you will see that it will be equal to x1 bar, right? x2 bar, x3 bar, x1 bar, x1 bar, all of them, because it's only one. The epsilon here, it will be equal to u1 and the c bar. Okay? So I take the average. The idea is if I take the average, now for now I will erase this one. Right? Now and I take the liberty of having a ruler here. I would take it over 1 over t, right? T equal 1 till t of y1t. Okay, this is nothing more than y1 bar. Equal to 1 over t summation t equal 1 till t of x1t transpose theta plus summation of 1 over t for t equal 1 till t of u1, okay, this is a constant, plus summation of 1 over t summations of c I t for t equal 1 till t. Okay? So let's say this one is equal to y1 bar, right? Equal to x1 bar beta plus u1. Because you sum t times u1 divided by t.
U1.
Plus CIT bar. So now I take each. I lost my pointer.
Huh?
I didn't eat it. I didn't have lunch. Somehow, somewhere in this time. Yeah. Don't worry. Always is down here. Now, ladies and gentlemen, now I take each each equation here. Now, have a look at. I take each equation here. I subtract this one. What do I get? I will get equal to y1t minus y1 bar. Here I have x1t minus x1 bar. I like the transpose here. Sorry. Transpose. Right? And then the u1 and the u1 here is gone. Okay? And the epsilon bar here, of course. So I can write it. I will have the new expression here. I will transform again. I am transforming, right? Let's take another color. Take a visual one, right? So this one, I would have it equal to y1 t minus y1 bar. Okay? Equal to x1 t minus x1 bar transpose beta plus, what is it? C I t minus C I.
I mean, that must be 1T.
That's correct. Thank you. One bar, okay? One bar, okay? Good. Good. So what do you have? You see that the unobservable characteristic is now gone. Okay? So you get rid of the endogenous term. See? Okay? This is now y2t, y1 t plus 1 minus y1 bar, right? Equal to x1 t plus 1 minus x1 bar transpose times beta. So for each observation now I have transformed them so that I get rid of the okay. So this is the new error term. This is the new explanatory variable. This is the new dependent variable. By doing this, I get rid of the fixed effect of the unobservable. That is considered to be fixed. Now, ladies and gentlemen, I'm explaining the terminology here. You want the individual specific effect here is assumed to be fixed, constant in each person. It represents his or her ability, right? So because we assume it is fixed, this kind of model is called a fixed effect model. Okay? This is a fixed effect. So if this is what you need to implement in Python, it will be too easy. Is that right? Now, there is a little bit of challenge here that you need to face. That is, now you are not going to compute over the whole data set, but the average value must be computed over the individuals. Is that right? Now, the bar here, the bar y1 bar here is not the y bar. So you have to compute the y1 bar, y2 bar, y3 bar for all of the cross-sectional units. Get it? Okay, so there is a little bit of challenge here, but other than that, you can implement this one in Python in no time. Right? So this can be an example in the. Okay. Now, another model that we often have is yt equal to it transpose beta plus ui plus cit. Okay? So this is a general model, right? So if we assume that the y and the ui here is correlated with the xi here, we have to follow the fixed effects model, right? Okay? if we assume that the UI is not correlated with the x here, they are random with respect to the x, we call it the random effect model. Okay? So what is the implication when we say that expectation of UI given xit is 0? That's to say, if you know the xi, you would know nothing about the specific effect, right? Of course. And of course, you have expectation of x c it given ui, and xit is also 0, right? If this is the case, this one is a composite error term, right? Composite error term. Now, so what is the expectation? And also the expectation of the assumption is of ui, uj given xi t xjt is 0 for I different from j. So if you know that someone is smart, you do not know if the other is smart. So the specific effects are not correlated. That is sometimes doesn't work. You can say, I know that Vietnamese people are hardworking. So if this is a Vietnamese, that is a Vietnamese, I think they are both good. That is to say, we have the cluster problem, right? And let's say generally within the Vietnamese, we are equally hardworking. Then the assumption that the specific effect of. So let's say we want to compute the, let's say in that case we put this one is epsilon it, okay? The composite error term. So let's say expectation of, let's say you would have expectation of epsilon it, right? Epsilon it plus j, what is it? Right, so let's say if we further assume that ui is normally distributed with mean mu and variance let's say sigma square u, and and the c it are normally distributed with mean 0 and variance say sigma square c. Okay? Now, so if we take expectation, so if you know these are the assumptions, if you take the expectation of epsilon it plus j, that is the covariance, let's say the covariance, okay, let's say this is the covariance, it is equal to, now, it will be equal to, because ui and u, let's say is to say it is equal to, what is it? The covariance. So it is equal to the expectation of, what is it? Ui plus psi it times ui plus psi it plus j. Okay? Yeah? Is that correct? Okay. So that will be equal to, what is it? Yeah, so let's say it will be equal to ui. Let's without the, because we always have a constant, right? So without the loss of generality, let's assume this one equal to 0. Because we have the constant anyhow. The constant will be mean everything, right? Good. So in that case, we would have this one equal to expectation of ui squared. Is that right? Because ui and epsilon I and C are not correlated. So they are 0 plus the expectation of C I T squared. So this will be equal to sigma U square plus sigma C
C square.
square. Okay,
Nhớ bên này.
correct?
Xong.
Now, so let's say, sorry, let's say for this is for, let's be very clear here. Let's say expectation, now expectation here of CIT plus J, right? And then let's talk about it. If J equal to 0, if J equals 0, that means they are contemporaneous, then this one will be equal to sigma squared. But if they are not contemporaneous, if J is different from 0, then it is equal to sigma U square is always there, plus sigma, plus the expectation of epsilon I times CT times CT plus J. We assume that they are IID, right? So, because let's say in that case, they are IID, so in this case, this one is 0. Okay? So you see that for each unit, the diagonal element is equal to this one. The off diagonal element will be equal to this one. Okay? So for one individual, you will see that you have the covariance matrix of the form, let's say you will have, I have a big matrix, right? I have a big matrix. And for the first observation, for the first person, I would have it equal to, the first one is 1, 1. So that is contemporaneous, right? So it will be sigma U square plus sigma C square. And then it will be sigma U square, okay? Sigma U square dot till sigma U square. Now I have overdone it. Let's put it very small. Dot here, okay? Then over here you will have sigma U square, right? The second term it will be the diagonal, so it will be sigma U square plus sigma C square again, and then it will be dot sigma U square. Okay, so dot here I have sigma U square. This one is all again sigma U square, and here I will have sigma U square plus sigma C square. This is for one unit. The next unit I will have it here, right? Over here it will be 0, 0. 0. This is for the first person, the first unit. The second unit I will start from here. It will be again sigma U square plus sigma C square, and so on and so forth. So you see that it will be the block, right? Over here it will be 0, 0, 0, 0 down here, 0 down here. So it will be like a block. So you will have a form like this one. Let's say I will write it in this way. So you will have a kind of a covariance matrix of this format. This is one. Oh no, this it can be better drawn, right? This is 1, 2, right? Let's say it must be fixed. 2, 3. Okay? 4. And would keep going. So these elements are the diagonal. You have sigma U plus sigma C. Off the diagonal you have sigma U, but around here they are all 0. So you have a kind of variance covariance matrix that has a very special form of, of variance and covariance. So this is actually, you can call this one omega, right? So in the end, you end up having, if the error term, so let's come down here, let's come back to the situation here. If the error terms, the specific effects here, ui, right, ui here, is not correlated with xit, then you end up having a model that has some form of heteroplasticity, okay, and some form of autocorrelation, right? So if you write a model, again we would define omega as equal to b transpose to the minus 1, okay? Then we will be able to apply the GOS again. So the panel, now I will not go to the dynamic panel, right? That would be take some but let's say these are the two basic models. The upper one here we call it the fixed effects model. The lower one here we call it the random effects model. And in principle, they are, if you do this one, you run the OLS again. It will be safe to do the OLS again. This one you have to do the GOS. But basically, they are just different way of doing the same thing. So that will be the exercise at home, right? So with that, I'm done with the promise on the econometric models. Now let's move on with something else. So I have uploaded the, I remember correctly, I uploaded day 4, oh, not yet day 5. Let me do it. Day 5, I'm copying this one. For the slides. To student slides. So what are we going to talk about in this session? So it's just some simple discussion. I have 26 more minutes to talk about this. Then we have a break. After the break, we will start with the data cleaning. Right? So now we are talking about a new topic, that is optimization. Okay, I'm going to upload it. Let me also, so let's say we have day 5 here, all of the model. I will also share with you the file that I have to check. So day 5, you don't have the, okay. The do file, the script file is also here, so I'm going to share it. In the day 4, I intended to have the, no, let's say the optimization. So on the day 5 here, you will have the optimization example. think it's better that I do this one also, to make sure that you get all the data that you need. So I have shared the data. So basically the idea for what we are going to do now is to say you have a very simple two variable function. Do you think that this one will have a maximize or a minimize? A maximum or a minimum? A minimum, right? Because if you go to either way, the square will lead to very high value, right? So it will have a minimum. And of course, we can we have some terminology here. But basically, the idea is you can solve for the first order conditions, and you can find the maximum point easily. Is that right? So because I write it this way, you see that the lowest number possible is that both of them are 0. So when both of them are 0, you have x star, that is the extremal point. For the x is equal to 2 and y is minus 2. So you know it, you know this already. Yeah. So but let's say the computer can will not know this. So you have to program it. So let's say, how do you want to? How can we proceed here? The software would know nothing about a maximum or a minimum. It just follow what we want it to do. So. Không ai đi xe máy không nè? Đi xe máy vừa mang cái bộ nghiệp đây để thầy vượt thầy. Okay, anyway. But the idea is, so let's say we come to I think in the you remember the so-called the Taylor series, right? So let's say if you the idea is this one. If you compute the first order derivative here, if it is positive, you know that if you increase the x, the value of the function will be higher. Okay? If it is negative over here, if you compute the value of the x, it will be lower, right? So the idea of the numerical optimization here is that, okay, so you compute the value of the gradient here is the value of the first order, and then you just allow a number alpha that is small to times that first order. So the function will move along based on the value of the first order, right? So if the first order is negative, it will increase the x a little bit. Negative, and negative is positive. Okay? If the value of gx is positive, it will minus the x a little bit. So let's say it will move. It will just so you will be given the first x, the first point of x for the software, and the software just would not know whether you are doing a maximum or a minimum. It doesn't care. And they say, okay, you compute the gradient vector, and then you will move it a little bit up or down. Depends on the gradient. Okay? If you are finding a minimum in this case, so if the gradient you know that you're finding a minimum. If the gradient is positive, meaning that if you increase the x, the value will be larger. That is not what you want because you are finding the minimum. So it will reduce the x a little bit. Okay? It will reduce x. So it will reduce the x a little bit, and until when the change in the x after some time, some iteration, the value of the function stay more or less the same. If it keeps changing the value of the x, but the function stay the same, then it said that I have found the place where I cannot make any further improvement. And in that case, it is to say that it has converged. Okay? So this is the idea that you imagine that this is the so-called the ISO you saw the gradient here, and for each of the so we are imagine that we have something like this one. Have a look here. So it's valve, right? So you cut into different sections. You will see you have all of the valve, the circles, right? The circles. Each circle here will have the same value on the vertical axis. Is that right? So if you start somewhere here, you will move up or move down. It depends on the value of the first order. Okay? So if you have that, you will see that you move further and further and further until when you go to this point, when the change in the value of the function is manageable, you start. What do I mean by manageable? We have to define it. Okay? So let's have a look at the right. So let's say this can be said to be the easiest, the most simple way finding a convex the minimum point on the convex function. So let's say we can program that in Python. Okay, so this is the idea, right? So I have a function. The function is x minus 2 to the power 2 plus y minus plus 3 to the power 2. So we define the function as in the slide. Fair enough? They are the same, right?
Mm.
We'll let me and then move on. Then we calculate the gradient
Mm.
factor. It is the first order derivative. So df over dx is this one, right? Partial f over partial x is this one. Partial f over partial y is this one. Fair enough? Then we will have a
Matrix.
matrix that contains dx, df over dx and df over dy. Actually, it cannot be pronounced d, but it must be partial.
Mm.
D is for the single variable, partial. So let's say you often see that we have dy over dx when y is a univariate function of x. But you have partial y over partial x1
Mm.
and partial y over partial x2. Remember that? So this is the partial derivative when the function is multivariate, right? If that is the case, then we define the search. So we have to input an initial point. The learning weight here is the alpha. Alpha is 0.1. The tolerant weight is 1 over a million. Meaning that if you keep changing the x, but the value, the change in the function is less than 1 over a million, you say that this is the maximum.
Mm.
You don't do that. You don't move further. The max number of iteration is 100. You allow the software to go 100 times. If after, let's say that now the idea is for k in the range of the max number of iteration, you calculate the gradient. The gradient is equal to, you give the point, right? Calculate it. So for the first element in the df over dx, you take the row, right? You take the first one, the second one. And the new point is equal to the point, that is the first one you give it. The second one, it will take the first one minus the learning rate times the gradient.
Mm.
Okay? And it will add them to the path the new point. So if the norm, that is to say the new point minus the point is smaller than the tolerance rate is here, right? So the length of the change in the point is less than 1 over a million. You print df converge after k plus 1 iterations, and you stop, right? And you put point equal to new point. In that way, you will get the value, right? So if I do this, I will have the result here. After 62 iterations, the actual or the minimum point is 1.999999 to minus 2.99999. So, is it close to 2?
Mm.
Yes. Is it close to minus 3? This is the idea of numerical optimization.
Mm.
The nice thing about this thing is sometimes you cannot have a closed form solution. You take the derivative and the function cannot be solved. That is all the case when you have to deal with the nonlinear models. Is that right? Okay. Now, in the previous, now I'm introducing all kind of. So basically, the principles will be the same. Now I am talking about. Let's say before we have the gradient descent, right? Now we are going to have the adaptive learning rate for the gradient descent. So in the previous example, what was the learning rate? Alpha was equal to 0.1.
Open one.
And you don't do anything. You just leave 0.1 and leave it there.
Mm.
So why 0.1? Can it be 0.99, 0.099? why only one? Right? So this is to say, yeah, you choose one number, so you see that there were 62 iterations, 62 times of calculation before the software can give you the extreme of y. Is that right? So now we have the adaptive learning, that is, we will define the value of alpha. Okay, so the value of alpha at each rate of iteration, we will solve for the mean of the variable equal to the function of xk minus alpha times the gradient. Okay, so we will hit the initialized value alpha equal to 1, the parameter like this one. Let's say every time you have a learning rate beta, and then it will be times with the alpha, it will times beta, and it produces the new learning rate, right? So the key difference here is the fixed step uses the same alpha in all iterations. The adaptive adjusts to ensure progress based on the current curvature. So if you do that, you will see that for the adaptive, basically you see what is the change. The change is that last time it converges after 62 steps. Now it converges after 2 steps. So it will be faster. And all of the computational guys, most of the time they are doing is how to program it in a way that you get the most efficient code, right? So that's the, let's say, so are we going to program ourselves when we do econometric analysis? The answer is no. We only do it when we have invented a new model, a new method, and we want to program it ourselves. Otherwise, we will use something that people have programmed because it saves time. We cannot do everything at the same time, right? But if you happen, at least some of you here, maybe still some will get a Nobel Prize in the future. Who knows? But if you are doing econometrics, and you see, I have found a new estimator that is very much effective. I want to code it myself, right? So then that is the time when your name is heard around the world, right? Now, one of the things is that you use the improved procedure, the estimate is almost identical. Exactly. There's no longer 1.99999 anymore. Because the 9 is so long that the software uses the full, the round number. Now I move to the new method. That is the Newton-Raphson method. Okay. Come on, I'm sorry. You guys are now in the 21st century and we are talking about something by a guy from the 17th century. Too simple. Why could he think of that? You should have thought of something else. Yeah. Of course, if he see an iPhone now, he would have kind of freaked out, right? Now, ladies and gentlemen, so the difference is mainly, now, ladies and gentlemen, the difference in this kind of numerical methods is mainly in the way you update, your solution. Right? So in the one before, people use the gradient. The gradient is a first order derivative, right? And the first one is very much naive. Just take alpha and give alpha a number, right? Alpha a number. The second one, okay, improve on it by saying every time I will choose the alpha new. That is adaptive. The third one say, now the gradient is too simple. Let's take the Hessian.
Hessian matrix.
Okay, that's the matrix. So the way I updated is I will take the initial point that you give me, updated by the inverse of the Hessian times the gradient. So there is a new term here. Instead of having alpha, now it is the inverse of the Hessian matrix. Is that right? Okay. And it will keep doing the same thing. It will keep doing the same thing all the time. For this very special case, you see that it is 1 over 2 times I because the Hessian matrix happens to be a because there is no cross term, there is no x times y, so you see that it has it is equal to 1 over 2 times the identity matrix. So this one is quite simple. And basically, look at this one. So what is the difference? The difference is that they have the new way of updating your initial guess, right? So you can give it any number, but it will. So let's say, how can we do that? In Python, right? So you have to define the function again, but then you use the Newton method. You have the initial point, the tolerance, the maximum number of iteration. Now it is to 10 because we know that it will converge very fast. You have the point, right? The initial point, and you have the path. So for k in the range max iteration, the gradient is equal to the gradient point. The Hessian is equal to the Hessian of the point. That's it. The step is equal to solve for this one, right? And the new point is equal to the point minus the step. Right. So again, if the change in the new point and the difference between the one numerical solution and the next is less, the length of that vector is less than 1 over a million, then we have found the maximum point. So I don't know if it's better. It also takes 2 iterations, and it gets quite exact numbers. These are the kind of solution. So beyond the, ladies and gentlemen, beyond the Newton-Raphson model and method, then we have the so-called, this one is quite the one that they use in Stata and in Python, right? So it is, the only difference is, again, is the way that you update the solution, the solution. So of course here, you will see that the VK is computed in a more complicated way, yeah? And the idea is that we do not want it to be more complicated, but the idea is that we want it to be more efficient. Right? So if this one has been provided by the authors, Broyden, Fletcher, Goldfarb, and Sano or someone. That is the method. Then the VK plus one is updated in this way, and the VK plus one is used again into this updating. Other methods is mentioned here, but basically the message I want to tell you is when you need to find the numerical method, the purpose is to update. You give it an initial point and you update it, right? So let's say now if we are here, and we do not want to give the initial point 0, 0. Let's give it now the initial point is 10, 10. Okay? What happens if I have 10, or let's say 100 or 1000? So we give a very weird and far away. Oh, what's happened? It's break time and I cannot work anymore. Come on. minus 100. We are doing something weird, okay? We make a big number.
Is it not? Is it minus 10,000?
Right, so let's say I want it to be right, so let's say in this case I want it to be let's take an example. Let's say this one. If I run this one, what do I get? Even if you give a different one, it will update quite quickly. So let's say, so but we have to say that this is a very simple example. So let's say there are many new methods. Just say basically the new methods are different in the way people try to update the initial one. So we come to something that we know very well, and we will discuss a little bit more after the break. I know that you are very anxious for the break already. I see that in your eyes. Please have let's say 15 minutes break. We have been very efficient in the